Imagine standing in a forest where dragonflies the size of eagles hunt overhead, where millipedes longer than your car crawl through the undergrowth, where scorpions, as long as your arm, wait in the shadows, with venom potent enough to drop any creature instantly. This isn't science fiction. This isn't a horror movie. This was Earth 300 million years ago. And if you think dinosaurs were terrifying, wait until you discover what came before them. Before you dive into this prehistoric nightmare, hit that like button and subscribe, because you're about to witness a world so alien, so utterly bizarre, that you'll be grateful you were born in the right era. Welcome to the Carboniferous period, the age when insect ruled supreme. Picture this. 358 million years ago, Earth looked nothing like the world we know today. The continents were slowly colliding to form Pangaea, a massive supercontinent that would dominate the planet's geography. But it wasn't the land, formations that made this era extraordinary. It was what lived there. Endless swamp forests stretched across the globe like a green, breathing organism. These weren't the forests we know today with oak trees and pine groves. These were alien landscapes dominated by towering club mosses and giant horsetails reaching heights of 100 feet or more. Tree ferns with trunks as thick as modern redwoods created a canopy so dense that the forest floor existed in perpetual twilight. Moss and primitive lichens coated every surface, creating a slippery, humid environment that dripped with moisture. The ground beneath was a treacherous carpet of decaying vegetation, creating vast peat deposits that would eventually transform into the coal beds we mine today. In fact, the Carboniferous period gets its name from these carbon-rich deposits. The air hung heavy with the smell of rot and plant matter, thick enough that you could almost taste it. But here's where things get truly strange. If you could somehow travel back to this prehistoric world, the first thing that would assault your senses wouldn't be the sights or smells. It would be the air itself. The oxygen revolution. The atmosphere during the Carboniferous period contained approximately 35% oxygen compared to our current 21%. This might sound like a small difference, but the implications were staggering. Those massive forests were essentially oxygen factories, pumping unprecedented levels of O2 into the atmosphere through photosynthesis on an industrial scale. For modern humans, breathing this ancient air would be like standing next to a constantly running oxygen tank. At first, you might feel energized, even euphoric, but within minutes, the oxygen toxicity would begin. Your lungs would start to burn. Free radicals would form in your bloodstream, attacking your cells at the molecular level. You'd experience nausea, dizziness, and disorientation. Extended exposure would damage your nervous system, potentially cause seizures, and ultimately prove fatal. But for the creatures that evolved in this environment, it was paradise. You see, oxygen is the fuel that powers metabolism. More oxygen meant more energy available for growth, movement, and survival. And when it came to insects, this oxygen abundance triggered something unprecedented in Earth's history. It triggered gigantism. Meganura, terror of the skies. In 1880, deep in a coal mine in Commentry, France, miners struck something unusual. Embedded in the ancient rock was a fossil so large and so perfectly preserved that it would rewrite our understanding of prehistoric life. When paleontologist Charles Brongniart examined the specimen in 1885, he gave it a name that reflected its most striking feature, Meganuropsis, later shortened to Meganura, meaning large-nerved in reference to the intricate vein patterns across its massive wings. Meganura was a dragonfly, but calling it a dragonfly is like calling a great white shark a goldfish with a wingspan reaching up to 28 inches, roughly 2.5 feet from wingtip to wingtip. This aerial predator was approximately the size of a modern hawk. Its body alone measured over a foot in length. Imagine walking through those ancient swamp forests and hearing a sound like helicopter blades cutting through the humid air. You look up to see a creature with 4 translucent wings, each as long as your forearm, beating independently with mechanical precision. Its massive compound eyes, occupying nearly half its head, provide almost 360-degree vision. Those eyes contain thousands of individual lenses, each one tracking movement with deadly accuracy. Then it sees you. Or rather, it sees movement. Meganura's wings weren't just large. They were engineering marvels. The dense network of veins acted like a structural framework, providing both strength and flexibility. Unlike modern dragonflies that can reach speeds of about 35 miles per hour, Meganura could potentially exceed 40 miles per hour in short bursts. It could hover, fly backwards, make hairpin turns in midair, and accelerate faster than almost any other creature of its time. Its hunting strategy was brutally efficient. Those powerful compound eyes would detect prey from up to 30 feet away. Within milliseconds, its nervous system would calculate trajectory, distance, and intercept course. Then it would dive, using those independently operating wings to make micro adjustments during flight. Its 6 legs, lined with sharp spines, would extend forward like landing gear, forming a basket-like trap. The moment contact was made, those spiny legs would clamp shut around the victim with enough force to crack exoskeletons. Powerful mandibles would then go to work, crushing and tearing with mechanical efficiency. Meganura needed to eat constantly, consuming roughly its own body weight every 30 to 45 minutes. Its diet consisted of other flying insects, early reptiles, and small amphibians that were unfortunate enough to venture into the open. What made Meganura truly dominant was its complete lack of competition. This was tens of millions of years before the first birds would evolve. Flying reptiles wouldn't appear for another 100 million years. The skies belonged entirely to giant insects, and Meganura sat at the apex of that aerial food chain. For roughly 50 million years, these sky titans ruled unchallenged. They were the F-22 fighters of their era. Fast, maneuverable, and absolutely lethal. Arthropleura, the armor-plated titan. If Meganura owned the skies, then Arthropleura was the undisputed king of the forest floor. And what a king it was. Discovered in fossil beds across Europe and North America, Arthropleura was a millipede-like arthropod that reached absolutely staggering proportions. The largest specimens measured approximately 8.5 feet in length and nearly 2 feet in width. To put that in perspective, imagine a millipede as long as a full-grown alligator and as wide as a coffee table, weighing an estimated 100 to 110 pounds. Arthropleura's body consisted of 30 to 32 armored segments, each one overlapping like medieval plate armor. This segmented design provided both protection and flexibility, allowing the creature to navigate through dense forest undergrowth despite its massive size. Its exoskeleton wasn't just thick, it was reinforced with calcium and other minerals that made it nearly impervious to attack. But here's the really fascinating part. Despite its nightmarish appearance, Arthropleura was likely a herbivore. Fossil evidence suggests its diet consisted primarily of decaying plant matter, spores, and possibly living vegetation. Its mouth parts weren't designed for predation but for grinding and processing tough plant material. That said, being a herbivore doesn't mean being harmless. Modern elephants are herbivores, but you wouldn't want to anger one. Similarly, Arthropleura's sheer size and armored body meant it had virtually no natural predators. Any carnivore, foolish enough to attack, would find itself confronting what was essentially a living tank. Fossil trackways reveal that despite its bulk, Arthropleura could move with surprising speed. Its numerous legs, estimated at around 64 pairs or roughly 128 individual legs, distributed weight evenly and allowed for efficient locomotion. As it moved, the rustling sound of hundreds of legs against dead leaves would have been unmistakable. Scientists believe Arthropleura could potentially move at speeds of up to 2 feet per second when threatened. That might not sound fast, but for a creature that size, it's remarkably agile. Imagine turning a corner in that prehistoric forest and suddenly seeing this armored behemoth scuttling toward you, its body undulating like a segmented train. Each footfall would shake the ground slightly, creating small tremors in the soft peat beneath. The sheer biomass of Arthropleura meant it played a crucial role in its ecosystem. As it moved through the forest, consuming dead vegetation, it essentially functioned as nature's composting system, breaking down plant matter and returning nutrients to the soil. In many ways, Arthropleura was the Carboniferous equivalent of modern earthworms, just infinitely more terrifying. Pulmonoscorpius. The silent death. Now we enter truly nightmare territory. Meet Pulmonoscorpius kirktonensis, whose name literally means breathing scorpion from Kirkton. This creature represents everything that makes our primitive brains scream danger. Reaching lengths of up to 28 inches, roughly the size of an adult human arm from shoulder to fingertips, Pulmonoscorpius was one of the largest scorpions ever to exist. But size alone doesn't capture what made this predator so formidable. First, let's talk about that name. Pulmonoscorpius references its possession of primitive book lungs, an early respiratory adaptation that allowed it to breathe air efficiently. This meant it could hunt on land, in water, and in the humid, transitional zones between them. Very few predators could match that versatility. Its body was covered in dark, chitinous armor with a texture like wet stone. This natural camouflage allowed it to blend seamlessly into the shadowy undergrowth of the swamp forests. Its coloration ranged from dark brown to nearly black, with lighter segments along its joints. But the real weapons were obvious: those massive pincers and that lethal tail. The pincers, or pedipalps, weren't just for show. They were powerful enough to crush the exoskeletons of other large arthropods and even crack the cartilaginous bones of early amphibians. Along their inner surfaces ran rows of small, sharp spines that prevented prey from escaping once caught. Imagine a vise covered in nails, and you'll understand what those pincers could do. The tail was a masterpiece of biological engineering. Each segment was connected with ball and socket joints that provided extraordinary flexibility and range of motion. The tail could strike forward, backward, or to either side with equal precision. At its tip sat the telson, a bulbous venom sac ending in a curved stinger as long as a human thumb. The venom itself was likely a neurotoxin cocktail designed to paralyze prey quickly. Modern scorpion venom is among the most complex biological substances known, containing dozens of different proteins and peptides. Pulmonoscorpius venom was probably similar but adapted for the large-bodied prey of its time. A single sting could immobilize creatures many times the scorpion's size within seconds. Pulmonoscorpius hunted through a combination of stealth and ambush tactics. Its 4 eyes, arranged in 2 pairs on the dorsal surface of its carapace, provided excellent low-light vision, but like modern scorpions, it also relied heavily on detecting vibrations through specialized sensory organs in its legs called pectines. These comb-like structures could sense minute ground tremors, essentially allowing the scorpion to hear through its feet. It would position itself in the areas of high traffic, near water sources, along game trails, or in narrow passages between fallen logs. Then it would wait, completely motionless, for hours or even days. When prey ventured close enough, the strike would come with frightening speed. The tail would arc forward, the stinger would penetrate the victim's body, and venom would be injected in milliseconds. Death or paralysis would follow within moments. In the food chain of the Carboniferous, Pulmonoscorpius occupied a crucial middle position. It was large enough to prey on smaller arthropods and amphibians, but also served as food for some of the larger predatory amphibians that dominated the aquatic environments. This made it a keystone species, helping to balance populations throughout the ecosystem. Megarachne. The spider that wasn't sometimes in paleontology. First impressions can be deceiving, and few cases illustrate this better than Megarachne cervinae. In 1980, Argentine paleontologist Mario Huniken announced a discovery that sent shockwaves through the scientific community and straight into the nightmares of arachnophobes worldwide. In 300-million-year-old rock formations in Argentina, he had found what appeared to be the largest spider ever to exist. The fossil showed a body length of about 13 inches, with a leg span approaching 20 inches. News outlets around the world ran with headlines like, "Prehistoric spider bigger than your head." For 25 years, Megarachne was presented in documentaries, books, and museums as the ultimate spider nightmare. Artists rendered it as a massive, tarantula-like predator stalking the Carboniferous forests, its 8 eyes gleaming in the darkness, its fangs dripping with venom. There was just one problem: it was all wrong. In 2005, paleontologist Paul Selden conducted a thorough re-examination of the fossils. What he found forced a complete reclassification. Megarachne wasn't a spider at all. It was a Eurypterid, commonly known as a sea scorpion, specifically adapted for life in freshwater environments. The features that had fooled scientists for decades were actually evolutionary adaptations for aquatic hunting. What appeared to be spider eyes were actually decorative patterns on its carapace. The structures thought to be fangs were actually modified swimming appendages. The body plan was distinctly Eurypterid, not arachnid. This discovery was actually more interesting than the original interpretation. Megarachne represented a lineage of arthropods that successfully transitioned from marine to freshwater environments, adapting to exploit the rich ecosystems of Carboniferous rivers and lakes. Its front limbs were broad and flattened, equipped with small grasping structures. These weren't designed for venomous attacks, but for raking through sediment and catching small prey items. Megarachne likely fed on small fish, aquatic arthropods, and anything else it could catch in the murky waters of ancient swamps. The crescent-shaped patterns and sharp protrusions on its dorsal carapace served multiple functions. They may have helped break up its silhouette in the water, making it harder for prey to detect. They also could have provided hydrodynamic advantages, helping direct water flow over their bodies during swimming. While Megarachne lost its title as the world's largest spider, it gained something perhaps more valuable: a place in the fascinating story of how arthropods conquered nearly every environment on Earth during the Carboniferous. The science of gigantism. So what allowed these creatures to reach such extraordinary sizes? The answer lies in a combination of atmospheric chemistry, evolutionary pressure, and basic physics. Insects don't breathe the way we do. They lack lungs and a circulatory system for transporting oxygen. Instead, they possess a network of tubes called tracheae that deliver oxygen directly to cells through simple diffusion. Air enters through small openings called spiracles, travels through increasingly smaller tubes, and eventually reaches every cell in the body. This system works beautifully for small insects, but it has a critical limitation. Diffusion becomes less efficient as distance increases. In modern atmospheric conditions with 21% oxygen, there's an upper size limit beyond which diffusion simply can't deliver enough oxygen to keep a large insect alive. But in the Carboniferous, with oxygen levels at 35%, that equation changed dramatically. The higher oxygen concentration created a steeper gradient, meaning oxygen could diffuse much farther into body tissues. Suddenly, the size constraints that limit modern insects simply didn't apply. Think of it like this. It's the difference between trying to drink water through a straw from a glass versus from a fire hydrant. The same mechanism works much more efficiently with greater pressure. Recent experiments have proven this connection. Scientists raised modern dragonflies in controlled environments with elevated oxygen levels. The results were striking. Dragonflies raised in 31% oxygen grew 15 to 20% larger than control groups raised in normal atmospheric conditions. While still nowhere near Carboniferous sizes, this demonstrates direct causation between oxygen levels and insect size. But oxygen wasn't the only factor. The absence of vertebrate predators was equally important. During the early Carboniferous, the largest land predators were still amphibians, most of which were confined to aquatic or semi-aquatic environments. The skies were empty of predators. This created a massive evolutionary opportunity for arthropods. Some scientists have also proposed the oxygen toxicity hypothesis. Paradoxically, too much oxygen can be dangerous. It generates reactive molecules called free radicals that damage DNA and cellular structures. Larger body sizes may have evolved partially as a defense mechanism, slowing the rate of oxygen absorption per unit of body mass and reducing oxidative stress. The combination of these factors created perfect conditions for arthropod gigantism, but as we'll see, those perfect conditions wouldn't last forever. The fiery apocalypse. The high oxygen content that enabled giant insects also created one of the most dangerous environments in Earth's history. With oxygen levels at 35%, the Carboniferous atmosphere was essentially primed for combustion. All it took was a single lightning strike. Wildfires in the Carboniferous weren't like modern forest fires. They were apocalyptic infernos that could consume thousands of square miles in days. The oxygen-rich atmosphere meant fires burned hotter, faster, and more completely than anything we see today. Trees would explode into flames from the sheer heat of approaching fires. The air itself would ignite in certain conditions. Evidence of these megafires is preserved in the geological record as massive charcoal deposits. Some coal seams contain thick layers of charcoal representing forests that were essentially cremated wholesale. Fossil studies show clear cycles of growth and destruction with layers of normal fossilized plants interrupted by charcoal horizons. For the giant insects, these fires represented an existential threat they couldn't escape. By the end of the Permian, oxygen levels had dropped to around 23%, and they would continue falling. For the giant insects, this was catastrophic. Their bodies, optimized for an oxygen-rich environment, suddenly found themselves in a world where every breath delivered less fuel. Movement became more laborious. The flight required more energy. Metabolism slowed. Giant insects became sluggish and vulnerable. But nature abhors a vacuum. As insects struggled, new predators evolved to exploit their weakness. Is the compressed remains of those Carboniferous forests. Forests that took carbon dioxide from the atmosphere and locked it away for hundreds of millions of years. In a sense, We're now releasing that ancient carbon back into the atmosphere, slowly reversing the work of those prehistoric plants. The irony is profound. The story of the Carboniferous also teaches us about the fragility of dominant species. Meganura ruled the skies for 50 million years, far longer than humans have existed. Yet changes in atmospheric chemistry and the arrival of new competitors erased them. Dominance in one era is no guarantee of survival in the next. So what would you do if you encountered a dragonfly the size of an eagle or a millipede as long as your car? The honest answer is that you'd probably panic, and rightfully so. These creatures occupy a space in our evolutionary psychology as wrong. The Carboniferous reminds us that evolution is capable of producing wonders beyond our wildest imagination, and that even the most successful adaptations are temporary solutions to temporary conditions. The giant insects are gone, but their story remains. It's written in coal seams and fossil beds, in amber and ancient stone. And it teaches us that Earth's history is far stranger, far more fascinating, and far more terrifying than we often realize. If you found this journey into prehistory fascinating, imagine what other secrets Earth's past is hiding. What would you like to explore next? The age of dinosaurs? The first animals to walk on land? The mass extinction events that reshaped life itself? Drop your suggestions in the comments below, and don't forget, hit that subscribe button so you don't miss our next expedition into deep time. Because trust me, we're just getting started.